In this video, we will be deriving kinematic equations from graphs. We're going to start off by making a velocity versus time graph of an object moving at a constant speed, with a constant acceleration, and it's going to have an initial velocity that is not equal to 0. So we'll have an initial velocity here, final velocity there, and our total time interval is some time interval t. I know several things about this graph. I know that the slope of the graph represents acceleration. I know that because the derivative of a velocity versus time graph is acceleration. I can also look at the units. When I take a slope, I do change in the y-axis over change in the x-axis. So the units of the y-axis are meters per second. The units of the x-axis are seconds. When we divide that, we get units of meters per second squared, which indicates the slope represents acceleration. We also know that the area under the curve represents the displacement of the object. We know that the area under the curve is the integral, and the integral of velocity versus time graph is displacement. So the area here is displacement. And we can look at our units once again. When we find the area of an object, we take a length times a width. So we're basically multiplying the units of our axes. So we have meters per second times seconds, which gives us meters. So those are the units of displacement. Using these two things, we can derive all of the equations that we need for kinematics from just the graph. Let's start off with the acceleration. We know that the slope is equal to rise over run, or change in y, over change in x. So if I know that my slope represents acceleration, I know that change in y is v final minus v initial, and I know that my delta x is this time interval t, assuming that t initial is 0. I'm just going to put a t there for the time interval. You could also put a delta t there. And that's our equation. We put little arrows over the symbols that represent vectors. Acceleration and velocity are vectors. Time is a scalar. So this is the first of the equations we're deriving. Acceleration is final velocity minus initial velocity over time. So we can use that to represent any situation in which an object is accelerating at a constant rate. We can also use our area. The shape of that area under the curve is a trapezoid. And the equation for a trapezoid is 1/2 times base 1 plus base 2 times t. Now, if we know the area is equal to the change in position, base 1 is this length right here. So that is v initial. Base 2 is this length here, which is v final. And the height is this length here, which is t. I messed up that. I got ahead of myself. This should be height. So that's our second equation that represents the motion of an object moving at with a constant acceleration. Let's include our little vector symbols. Displacement, velocity are vectors. Once again, time is a scalar. Now I can use these two equations to derive my other two equations. The first thing we're going to do is derive an equation in which time is not a factor. So we're going to solve this equation for t. So I just rearrange it. I get v final minus v initial over a. And then I'm going to take that and I'm going to plug it in for the t in this equation. The result will be an equation that does not have t in it. So if you have a problem and you're not given t, you'll be able to solve for some other variables. So we have delta x is equal to 1/2 times v initial plus v final times t, which is v final minus v initial over a. Now on here, we have v final minus v initial times v final plus v initial. So we know that that is going to give us, I'm going to move the a with the 2, v final squared minus v initial squared. And then we're going to rearrange this a little bit. So we'll do 2a delta x equals v final squared minus v initial squared. The most common form you see this equation in is this one, v final squared equals v initial squared plus 2a delta x. So we have our final velocity squared equals our initial velocity squared plus 2 times the acceleration times the displacement. That is our third kinematic equation. Let's derive another equation, and this time we're going to take out final velocity. So once again, we have the equation acceleration is v final minus v initial over t. That's our slope equation. And then our area equation was delta x equals 1/2 times v initial plus v final times t. So this time, I'm going to solve this equation for v final. So we get v final equals v initial plus at. Forgot these. And we're going to plug that in here. Sorry, that's sloppy. Plug in, and then we get delta x equals 1/2 times v initial plus v initial plus at times t. So here, this gives us 2v initial, but then we multiply by 1/2, so that will go away. And we get delta x is equal to v initial times t plus 1/2 at squared. And that is our fourth kinematic equation. We derived them all from the graphs, which means if you understand the graphs, you do not need to memorize any equations. You can solve any kinematic problem.